Hello, everyone. Welcome to this week's edition of the HoloTube seminar series. We today are very happy that Ben Freivogel has agreed to join us and tell us about quantum corrections to black holes from semi-classical gravity. Please take it away, Ben.
Okay, thanks for having me. Yeah, so I had to look through some of your previous talks, and yeah, I see that this is not quite in like the main line of what you guys have been hearing about. So yeah, please just interrupt if you have questions about the context and so on. Basically, I tried to prepare kind of like the minimal amount of material. I don't know where you guys are, but I have a certain Zoom fatigue at this point where I can learn small amounts of information on Zoom. So I tried to minimize the amount of things that I prepared, so there should be time for questions and so on. So please just jump in if you have questions. That will also help me, get things communicated in the right way. Okay. So a physics question that we might be interested in is to what extent observables outside the horizon are sensitive to the black hole microstate. So suppose you consider black holes in two different possible microstates, psi1 and psi2. And let's just consider the expectation value of the observable. Okay, that's the type of quantity that I want to discuss. But first I want to know people's prejudices. So does somebody have an opinion about how large this quantity should be? I'm not going to really take no for an answer. So I need at least like one answer for how large this type of thing should be. We'll see who's the weakest link, and we'll give in and give an answer. No, I mean, you think I'm joking, but I taught high school in the past, so I will actually wait till you tell me an answer on this question.
It's definitely less than the bound given by the triangle inequality, right?
Okay, so let's see. So there's some triangle inequality. Yeah. But I guess that would be some order 1 type bound, most likely. I mean, potentially. Other comments? Well, okay, I still have the hope of getting more opinions from you, but let me just mention a little bit more context. So, I mean, this is kind of an important quantity for asking whether quantum effects are visible outside black holes, right? Because classically, you have no hair theorems. So it would kind of say that observables outside the horizon don't care about the quantum state of the black hole at all. But quantum mechanically, we don't have those theorems. And in fact, the information has to get out of the black hole. So some observable at some time needs to know something about the quantum state of the black hole. Right? If you form black holes by collapsing two different pure states, then the radiation has to be different. So there's a bit of a tension there. I think that the two answers that you might get for this kind of quantity are, some people would claim that this quantity is like e to the minus s, where s is the Bekenstein-Hawking entropy of the black hole. But people who have thought seriously about how to kind of build models of how information gets out of the black hole. So models like the so-called nonviolent non-locality of Giddings. These models will typically have this quantity being some order 1, either a 1-point function or a 2-point function near the black hole. Will differ by order 1 depending on the pure state. Roughly, that's because the information is coming out in the Hawking quanta, right? Those Hawking quanta are have wavelength of order the black hole at a distance of order 1 horizon radius away, and they're carrying the information. So you have these modes whose wavelength is similar to the black hole, and the state of this mode depends on the state sign. Okay, so because those modes are going to carry the information out. So there's really like a very large variance in the theoretical expectations for this quantity. Good. So what is the basic claim? I mean, if somebody wants to say that we don't care about this quantity or whatever, then go ahead. Please speak up at any time. So the claim is that we can't compute this quantity. But we can compute an average. Okay, so we're gonna introduce a weird quantity called the quantum deviation. So right now I'm just giving the basic outline, and I'll describe this in more detail. So that quantum deviation depends on the operator that we're talking about, and it also depends on having an ensemble of pure states. You can also have an ensemble of mixed states as well, but for this talk, let's just specialize to the case of pure states. So this quantity that we're going to be interested in, what we do is we average over the pure states with some probability distribution, which I'll just write as f of psi. And then I calculate the expectation value in these pure states. I take the absolute square of that so there won't be any cancellations. And then I just subtract off the average value of this thing, averaged over that ensemble. Okay, so it's basically like a variance in expectation values. There's of course other ways. There's more general ways that you could probe how sensitive operators are to pure states, to the quantum state of the system. This is just something that we found convenient. So the key point about this quantum deviation, first of all, it gives information about the sensitivity about the sensitivity of some operator to the quantum state. And the main point is that for certain ensembles of pure states, we can calculate this in gravity. And so basically this is going to give us a tool. As you'll see, it hasn't been used in all of the ways that we would like to use it yet. But so this will give us a tool for kind of constraining these competing claims about the size, about the sensitivity of these operators to the quantum state of the black hole. Okay, so it should give us a way to compute and to differentiate between these different theories. Okay, so that's the basic thing that I want to do. To put it a little more in context, you've probably all heard about how we can now successfully calculate the entropy of the Hawking radiation. And this has been calculated basically in gravity by including new saddle points, right? So by including replica wormholes. I'm not going to review that in detail because what we're doing is not really like technically very closely related, and also you've probably heard about these developments. But so those were very exciting theoretical developments where people could calculate the entropy of the Hawking radiation, of course, like in certain theories. But we kind of want to focus on the more, let's say, slightly more practical question of, okay, that's great about the Hawking radiation, but say we want to think about actual observables outside the black hole. To what extent are those things sensitive? How do we calculate quantum gravity corrections to those things? So we kind of want to extend these techniques beyond just calculating theoretically interesting but observationally obscure quantities like the entanglement entropy. And another related point is that mostly these calculations rely on having an ensemble of theories, and we're extending this. We're going to just have this ensemble of states. So that's going to extend these kind of developments to situations where there's no obvious ensemble of theories to average over. Okay, so I can tell you a little more concretely about all of these points, but let me just ask, so is it clear what question we're trying to answer and why I care about that question? Or are there questions at this point?
Can I ask a question?
Yes.
Oh, is there any specific psi function for which this variance becomes zero?
Well, I think that for a given operator, there would certainly be functions like that. So like if the operator is the Hamiltonian and then maybe that function localizes on energy eigenstates, then the variance will probably be zero, something like that.
I see. Okay.
I don't know if that's technically in detail true, but yeah. Our point of view is more to think about like physically motive. We're going to need to pick some particular F so that we can actually do this computation. In particular, to be able to calculate it in gravity, we're not going to really be able to pick our function very generally.
Okay, thanks.
Other questions? Okay, so the plan for the more detailed part of this talk is to just, first of all, because it's a little bit of an unusual quantity. So I want to first just talk about this quantum deviation, just in quantum mechanics. Then I'm going to come to particular ensembles of pure states. So some f of psi, where this quantum deviation is related to a correlation function in the thermal field double state. So that's going to be like a field theory result. And then we're going to come to the gravity dual. Okay. So yeah, first of all, my point about quantum mechanics is that this quantity is a strange quantity in quantum mechanics. Okay, and to see this, we're going to look at a very the simplest possible case. So let's look at 1 qubit, or spin a half particle. And we're going to consider 2 different probability distributions. Okay, so we're going to consider, and this is going to be a bit pedantic, but everything will extend to the more general case. Okay, so it's not going to be any wasted effort to understand this simple example. So let's consider one ensemble of pure states, which is simply that the state is either spin up along the z direction or it's spin down along the z direction, each with probability a half. Okay, that's a pretty boring ensemble of states. Let's also consider f omega, where psi is equal to up along some direction n with equal probability on the Bloch sphere. Okay, these are 2 different ensembles of pure states. The reason I said this is a strange quantity is that a lot of times what you would do if you have an ensemble of pure states is you would calculate the density matrix, which in this case I'm going to call rho 1 for reasons that you'll see. So you can form the density matrix in this way. And probably you can see that for these 2 different ensembles, the density matrix is the same. It's the maximally mixed density matrix. Okay, so even though these are 2 different ensembles, they have the same density matrix. And that means if all you get to do is access one system at a time, then you can never tell the difference between these 2 systems. All right, but this quantity that I'm looking at, and let's consider a simple operator here. Let's consider the operator O equals sigma z. So my statement is that the quantum deviation of this operator is different in these 2 ensembles. If you remember, in the quantum deviation, there was a, well, let's maybe write the definition again. So this quantum deviation is given by integrating, by averaging over these states, the expectation value minus its average. In both of these ensembles, the average of sigma z is 0. So this term is 0. So it's only a question of these states. Now you can see that in this ensemble that I called Fz, the system is either spin up or spin down along the z-axis. So the expectation value of sigma z is either 1 or -1. And so the square of that is 1. So this is equal to 1 in this distribution. And it's equal to, well, I forget, but I think it's a third in this other ensemble, right? Because in that other ensemble, for example, you might have spin up along the x direction. And in that state, the expectation value of sigma z is 0. And I think that probably if you suitably average, you'd probably find 1/3 for this quantity. Okay, so I mean, this is a boring thing to do with qubits, as far as I know. But you know, when we're thinking about black holes, okay, we can't do all of these computations explicitly, but we are very interested in, once you average over an ensemble of pure states, how do these expectation values differ over that family of pure states? Okay, and the difference is not going to be a question of 1 versus a third. It's going to be a question of, you know, 1 over s, e to the minus s, e to the minus s over 2. So we're going to get like very large possible differences in the answers. Okay, that's the kind of the quantum mechanics introduction to why this is a well-defined but weird quantity. Are there questions? Okay, I want to mention one more thing at this quantum mechanics level, which is that this quantum deviation, it can't be calculated from this usual density matrix, but it can be calculated from something that we'll call rho 2, which is like a density matrix in a doubled system. Okay, so given some ensemble of pure states, we can define rho 2 to be this integral, but now we take 2 copies of the state. And now this quantum deviation is simply given by the expectation value. So let's maybe label these two copies as left and right, just to be definite. The expectation value, this quantum deviation is just given by the trace of rho 2, and then we need to put O left and O right dagger. And you can kind of think about it like, if you want to be able to do this type of measurement on this ensemble of pure states, you need to be able to access like 2 copies of a given pure state at a time to do these types of measurements. Okay, so that if the person preparing this ensemble is willing, then you can do this measurement. All right. So basically the situation now we want to extend this to gravity and so on. But first we're going to extend to quantum field theories. But so basically we want these rho 1 and rho 2 to have nice gravity duals. Okay. Any last question regarding quantum mechanics?
I have a question, Ben, sorry.
Yes.
Can we also compute, for example, the entanglement entropy of right side or left side for these 2 different f functions, and then see whether they are different from each other or not?
I didn't really think about that. It's certainly true that this density matrix that I'm constructing here is certainly entangled. Yeah, okay, that might be interesting.
Okay.
Other questions or comments? All right, so let me say a little bit about what ensembles we want, pure states we want to think about and how that's going to connect to black holes. So any state, of course, we can write in terms of the energy eigenbasis. Okay, so these n's are going to be energy eigenstates. And so if we want to give a probability distribution over pure states, we just need to give a probability distribution on these psi n's. So one way to specify the probability distribution is by specifying, you know, the endpoint functions of these psi's. Okay, so now we're just doing, so we have some f of psi, right, which gives some, right, it gives a probability distribution. So for simplicity and for reasons that you'll see, so what we're going to assume is that we don't actually care about the phases of these guys, but we're allowed to care about the amplitudes. Okay, so we're going to assume that f of psi doesn't care about these phases. If you think about it, in a chaotic system, that's actually saying that the system, the probability distribution is time translation invariant, because when you do a time translation, then these psi n's go to psi n e to the I e n t, right? And in a chaotic system, these energy eigenvalues are not correlated in any simple way. And so under time translation, then these phases change. So if we assume our probability distribution is invariant under a phase rotation, then that will imply that it's invariant under time translations. It's basically because we want to consider ensembles where you know, the state has roughly a particular energy, but we don't particularly care about the phases. Okay, so we're going to have an invariance, which is psi n goes to e to the I phi n psi n. Okay, that's enough. So now we're going to use this kind of weird double bracket to mean an average over this space of states. Okay, so once you have this invariance, that's enough to tell you that this psi expectation value of psi n has to be 0. And the 2-point function has to be diagonal. And then we can put some probability here. And we don't actually need to specify our full probability distribution, but for our purposes, we are going to actually need to know the 4-point function. So the 4-point function in this ensemble of states, so it's going to be kind of, you know, it's going to be diagonal. So there's going to be a delta nj, delta ml, in order for this phase invariance to work. And then some general Q and L. Okay, I'm going to spare you most of the details about how we had to choose this thing, but that's actually a lot of the work that we had to do, is to find a nice ensemble of states. Let me first maybe just mention an example, which doesn't quite work, but it was the example that kind of inspired us to look at this. And an example that we looked at was a microcanonical ensemble. Right, so there you kind of have the feeling that there is a natural average over states, right? You just restrict to some band of energies, and then you can take f of psi to be the unique unitary invariant measure on states. Right, for example, you can start with a reference state and you can act with unitaries that are hard random, and that will give you an ensemble of states. So in this microcanonical ensemble, so what is that telling you? So it's basically saying that these PNs are equal to like 1 over D, where D is the dimension of the Hilbert space, for En in the energy window. Okay, so that's a very concrete ensemble where you can calculate all every order of what this probability distribution is. And we kind of started with this ensemble because we were inspired by some work by the UBC group. So Pollock, Rosali, Sully, and Wakeham, who kind of introduced this idea of averaging over states in this context. Now, so the microcanonical ensemble, that's a nice ensemble of states. And you can see that the original question that I asked makes sense in that context, right? We consider an ensemble of black holes, a microcanonical ensemble of black holes, and we ask how much of the expectation value of some observable outside the horizon depend on the microstate. That's perfectly well defined thing in that context. But the issue in this case is that this row 2, which is basically gives our technique for computing the size of this quantum deviation. In that case, this row 2 doesn't have a nice gravity dual. And to see how we can fix that, I need to give a little bit more details of how we're going to look at this row 2. Okay. So there's some details that, as I said, are mostly what we worked out in our paper. But the details are about how to fix this 4-point function. Those are very interesting technical details, but I don't think it's going to be that interesting to include in this talk. Basically, the question is, so we're going to be interested in this probability distribution being something like an ensemble of pure states, like a canonical ensemble of pure states. But there's not actually, even though it's obvious what the ensemble of pure states is, that corresponds to the microcanonical ensemble, it's not very clear what's the ensemble of pure states, or what criteria determine the ensemble of pure states that corresponds to the canonical ensemble. Okay, but what we have is an ensemble of pure states that computes a quantity that we're interested in and that we can compute in gravity. So we have kind of like a practical approach here. So, okay, so sorry about that. Skipping over these details. So there's some choice of these things. What we find for our density matrices. So you remember this row 1 is the boring thing. It's just when we, when we just integrated f of psi. So that becomes just the sum over these probabilities of something like this. Okay, so you can there you can easily see that depending on how you choose these probabilities, you can make this so choice of these PNs. Then this can lead to canonical, microcanonical, whatever. Okay, but to compute this deviation, Then we need to compute this row 2. And in this case, it turns out to be kind of a trivial thing, which will be subtracted off when we compute this quantum deviation. And then a non-trivial thing, which looks like this. And then some terms that are suppressed by some e to the minus s. Okay, so at this point, we need to be at large entropy. That's very natural in this context. Okay, so this term is basically going to be boring. That's going to be subtracted off. The non-trivial thing is this thing. And okay, unless you know things that I don't, then this doesn't have an obvious gravity dual. But what we're going to do is instead write this. So let's kind of ignore this factorized piece. So this piece here, we're going to rewrite it as these probabilities. And then we're going to write n bar, m bar, and then we're going to write a partial transpose. Okay, so this is kind of a crazy thing to do from the point of view of just manipulating equations. But you can see that now, if you define a state T, which is going to be a thermal field double-like state, and that state is going to be Pn n bar. That's not quite normalized. So we need to divide by square root of the sum of the pi squareds. So for some choices of p's, this will be a normal thermal field double state, but it's sort of like a generalized thermal field double state. And the point of the thermal field double is that we know what the gravity dual of the thermal field double is, right? It's the eternal black hole. Okay, so for some choice of p's, T is thermal field double. And this is dual to the eternal black hole. Whenever you define this thermal field double state, there's these annoying bars that I put over the end that have to do with some anti-unitary. Let's ignore those details. Okay, that's again worked out in the paper, but that's not any original kind of complication for this project. That's just the usual annoyance of the thermal field double. Okay, so once you put all of these things together, what you find is actually a very simple result. So this is now just a field theory result. So quantum field theory, or even a quantum mechanics result. So for suitable, probability distributions, which we have worked out the details for, then the quantum deviation for any operator that's at all reasonable is given by this correlation function in this state T of a. So this is a state in a double copy of the system, right? And because we did this weird partial transpose, then this O right, it's not going to be the dagger anymore, but it's going to be a star. So something that's related to the dagger by conjugating by this anti-unitary operator. Okay, it's basically just given by this 2-point function in this thermal field double type state, up to this normalization that appeared here in T. So outside we have the sum of the pi squared. Okay, and you can kind of see that this factor is like the purity of the density matrix. well, anyway, it's related to the purity of density matrix. Okay, so this is the result. I don't know if you would care about this result outside of gravity. So, but it is kind of nice that there's a simple correlation function in a thermal field double type state that tells you about how much some operator fluctuates. How much does its expectation value fluctuate in an ensemble of pure states? Okay, so that's the quantum field theory result. Are there comments or questions? Yeah, so just to repeat, so these probabilities are related to our probability distribution by, these are just the 2-point functions. Okay, so that's the general result. So now let's talk about when does, all right, so now we come to gravity. Okay, so when does this?
Oh, sorry, Ben, I have one more question. Is it true to say that two different f of psi function have definitely two different spectrum of PNs? Or is it possible to find, for example, two different f of psi functions with the same spectrum of probabilities or not?
Yeah, so it's kind of weird, but you should think of, so these psi n's, of course, they're the amplitude to be in some state. But for me, it's easier to just think about it from the point of view of like probability. So F, let's pretend there's a finite number of energy eigenstates. So then you're just giving a probability distribution over some complex vector psi n.
Mhm.
And what I'm specifying here in this equation with these PNs is kind of only about like the 2-point functions of those psi n's.
I see.
So that doesn't fully specify the probability distribution.
Okay. Thanks.
Yeah. So what we did is to ask the question of, given these, you kind of have some physics that tells you what should specify this 2-point function, because maybe you want to think about the canonical ensemble or whatever, right? But there's not obvious physics that specifies the higher point functions. And so we tried to think about like what's a natural ensemble of pure states. And the criterion we ended up using is that ensemble should be such that the function f maximizes the entropy.
Excellent.
The entropy here in the sense of normal like Shannon entropy, of a function on of a probability distribution. So that's kind of nice from a math point of view. I don't know if you have to do it from a physics point of view.
Thanks.
Any other comments? Okay, so now just to say briefly, so that's the quantum mechanics quantum field theory result. So now obviously what we want to do is we want to consider this in the ADS CFT context, where T has a gravity dual, and in particular we want that gravity dual to have a black hole. Okay, so and let's remember that our usual density matrix that defines the average over these states is just the sum of Pn. So it's diagonal in the energy eigenbasis that came from our assumptions about the time translation invariance. Good. So, right. So let's consider these different Pn. So one Pn we considered is microcanonical. I told you that didn't have a nice gravity dual, but now I can tell you why. So this thermal field double like state is equal to some normalization that is not so important for the moment. And then we have Pn and n bar. So this is kind of like a microcanonical. What is it? Oh, I'm sorry. I don't know what I did there. A microcanonical TFD, or a microcanonical field double. I forget what, something like that. So it's kind of a microcanonical version of the usual TFD. There's a paper by Merrill that discusses this. And if you read the paper very carefully, what you find out is that this has no nice gravity dual. The basic reason is that the only candidate gravity dual is the eternal black hole. But in the eternal black hole, you can calculate the fluctuations in the energy. And they turn out to be too small. I mean, basically the issue is that the microcanonical ensemble, the uncertainty in energy, the width of the energy window should be smaller than the temperature. But if you do computations in the eternal black hole, you find fluctuations in the energy of order the temperature. And so black hole, you find delta E of order t squared. And so those things don't, sorry, this wasn't the clearest explanation ever. Okay, but anyway, the fluctuations in energy are too small in order for this thing to be dual to the eternal black hole. So you have to do something more exotic. But okay, we're not particularly attached to the microcanonical ensemble. So we can take Pn to be canonical. So 1 over z eta minus beta En. So some canonical ensemble. And then this state is just some normalization factor times e to the minus beta En and n, which is the usual thermal field double state, but actually at the temperature 2 beta, or inverse temperature 2 beta, because of the usual definition of the thermal field double. But this thing has a gravity dual. If you don't like, so then that's a context where we can ask this question, okay? So we can consider an ensemble of pure state black holes. And we can calculate these fluctuations. Of some operator that we're interested in. And then that's related to just a 2-point function in the eternal black hole. Well, I'm writing TFD, but you know that that's equivalent to some gravity calculation. Times a normalization factor. And that normalization factor, if you remember, was this sum of pi squares. In this case, it's a little more natural to write that in terms of the partition functions at different temperatures. Okay, and this thing we can calculate in gravity. So that's kind of the main point that we wanted to make, is that there's a quantity that seems like it's hard to calculate in semi-classical gravity, which is the information about how different pure state black holes look different outside the horizon. And the claim is, in the context of ADS CFT, we can actually calculate this quantity. Okay, we can calculate this 2-point function with the gravity calculation. Let's maybe, well, I guess I want to mention one other possible ensemble, which is maybe a little bit more natural for this, I'm not sure. So we can consider a window of energies, which is much larger than the temperature, so that we'll have a nice gravity dual. But it can be much smaller than the window of energies that you have in the canonical ensemble, which is square root of the entropy times the temperature. In that case, if this window of energies is sufficiently small, then this thing takes a slightly more intuitive form, which is just this prefactor is just some e to the minus s at that energy. And then here we have a black hole with temperature E, and we have a 2-point function in that eternal black hole. Okay, so if we consider some ensemble of black holes with energies around this energy E, then we can calculate the size of this deviation here. Okay, I want to apply this to a particular case, but are there questions at this point? So before I apply it to a particular case, you can kind of see what's likely to happen here. If you pick kind of boring operators outside the black hole, so boring operators. I mean, we're interested in boring operators to some extent because, you know, LIGO is sensitive to boring operators. If we just pick boring operators outside the black hole, then this 2-point function will be some order 1 thing. And then that means that this quantum deviation will be e to the minus s. If you remember the definition, that means that the typical size of this thing in a pure state that will be like e to the minus s over 2, right? Because this delta squared is like a standard deviation. So it's like the expectation value of the square. So when you take the square root. So this gives something like e to the minus s over 2. So it's bigger than the most conservative. But it seems to contradict some of these more ambitious, or some of these more concrete proposal for how the information gets out. Okay, I still actually need to kind of discuss with Steve Giddings in more detail, like, you know, are there any loopholes for the operators he's interested in considering? Can there be some subtleties in the bulk to boundary mapping or whatnot that would allow you to escape from this conclusion? All right, but so that's why I'm not advertising this more, but there's a suggestion that this kind of computation is going to tell you that you can't have order 1 corrections to correlation functions outside the black hole. Okay, let's apply to a famous operator, which is the long time correlation function. Right, so the point that Maldacena made is that if you compute the expectation value of O in gravity, then this goes to 0 as t goes to infinity, because things fall into the black hole. And small corrections don't fix that. Perturbative corrections to gravity and so on. On the other hand, by general reasoning, we know that at least on average, this A of t, A of 0, it has to be larger than e to the minus s, because there's only e to the s states available. And so correlation functions can never decay below e to the minus s. Right, so this is one version of the information problem. So let's calculate the quantum deviation for this operator. Let's maybe do it in this mesocanonical type ensemble. So here we have e to the minus s of e. And then we have a correlation function in the black hole background. We have a left of t, a left of 0, a right of minus t, a right of 0. And this correlator actually ends up, you have to be a bit careful about the orderings and so on. But the ordering ends up being that this correlator actually just factorizes into two 2-point functions. So this thing just becomes order 1 at large t. Okay, so this is kind of an exotic observable, this long-time correlation function. But what you see is that it's sensitive to the state. And the typical value, right? Remember that this thing is, so I wrote it as the average over f, but now let me use this ensemble. So we did an ensemble average of the expectation value of our operator squared minus the disconnected part. And this thing gives e to the minus s. And so that's actually telling you that in a typical pure state, this expectation value is at least of order e to the minus s over 2. Now, we're confused for a little while because there's this famous story about the spectral form factor. Sorry, I'm almost done here. Spectral form factor is closely related to computing the following quantity after kind of stripping off the details related to the operator. But this long-time correlation function in a mixed state, in the thermal state. This thing goes like e to the minus s at large t. And this has a whole nice structure of a slope, a ramp, and a plateau. So that's all very nice. But actually what our computation is telling you is some slightly different physics, which is that if you look at any pure state, this correlator is actually much larger, e to the minus s over 2 instead of e to the minus s. That's kind of relevant because, you know, black holes that you form in collapse have a relatively small entropy. And so this computation in the thermal state is not necessarily relevant. Okay, so actually the expectation value in typical pure state is much larger than this beautiful physics that's been computed with a spectral form factor. Okay, let me kind of very briefly summarize and wrap up. So the basic claim, I think you know by now, which is that we can calculate something that you could call quantum gravity effects, right? Deviations of pure states, deviations of pure state black holes from the average. And we can calculate that using gravity. Or, you know, semi-classical gravity. Now, there's many things that need to be done. The more concrete things are to, you know, constrain models of black hole evaporation. But more generally, you know, we could tell this whole story because we had this nice ADS CFT framework where you can have a nice ensemble of pure states and so on. But really, we'd like to be able to extend these techniques beyond ADS, right? This also goes more generally for this whole story about replica wormholes and so on. I mean, really, we want to compute quantum gravity effects in you know, cosmology. Okay, but maybe before going there, we should maybe think about just black holes in flat space. And the most obvious question there is, you know, what is the ensemble that we're thinking about? And then, of course, you know, this is coming to the basic question of, you know, are there observables that are sensitive to quantum gravity? Right, black holes were like a case where observables might be sensitive to quantum gravity because you know that our usual expectations about when quantum gravity becomes important are somewhat modified near black holes. But that's kind of the big picture question, right? Do we have a chance to test quantum gravity in some observational situation? And that's kind of what I'm working towards. Okay, thanks.
Thank you very much, Ben. So we had a few questions during the talk, but are there more questions? You mentioned earlier, Ben, that you had selected like a minimum set of material or amount of material to present. So if you had a little more time, what is there anything yet that you like would want to mention?
I don't know if I have anything very brief to mention. Yeah, there's various details about. I mean, I don't know. The thing that would be interesting to discuss, I guess, is like, you know, we used to fail at computing the entanglement entropy from semi-classical gravity, right? And now people can do that. And so now we should be able to answer every question about optimistically, we should be able to answer every question about the size of quantum gravity effects. But as a practical matter, that doesn't seem to really be working right now, right? Because like we don't, you know, there are some papers where people tried to calculate quantum gravity effects in cosmology, right? Like there's some paper, the Brockett wormholes by Maldacena and so on. But I don't think we really know how to do, I mean, those were like very speculative and also to some extent in 2D. I mean, they're very interesting, but yeah, maybe the question is, yeah, to what extent can this become kind of there's like a slogan, which is, you just need to consider all of the gravitational saddle points for the computation that you're doing, right? And when we're calculating entanglement entropy, we were missing some saddle points. So it seems like we should be able to apply that slogan much more generally. But yeah, so I'm curious if people have thoughts about that.
Yeah, this is not an easy subject for sure.
Yeah, I guess in general, we're not very good at even knowing, like, we're not too bad at finding saddle points, but then we're not very good at knowing whether they contribute and so on.
Yeah, well, are there any other questions? I just kind of gave you some extra time to share your thoughts, but that's all right. So if there are no more questions, then I'll just stop the recording. Thank you very much again, Ben.
All right, thank you.